This is lecture 2 in X-ray series. So, Photon emitted the patient interaction, attenuation, and remnant beam. So, welcome to RadSound FRCR Physics. Remember our approach where we start with the source, patient, signal, detector, image formation, optimization, and safety control. In lecture 1, we created the X-ray beam inside the tube. In lecture 2, we're going to follow that beam into matter. So, when the X-ray leaves the tube, from the tube to the image formation, so to patient, detector, and to the image formation. While the photon enters patient, several things can happen, and that image depends entirely on what happened next. That can be transmitted, absorbed, and deposited, or scattered. So attenuation is a process of all in all a reduction in primary beam intensity due to absorption scatter out of the primary beam. The image comes only from the photon that passed through without interaction. So now we have transmitted primary beams. So the useful image or information comes only from the transmitted primary photon. So anything that passes, this is the patient, okay? So anything that passes through the body and reaches the detector. But what about a scatter? We're going to discuss about what's happening with the scatter, because scatter is carrying misrepresentational or mispositional information. So scatter will not add information to the image, rather it is going to add fog or decrease the contrast of the image. So remember this concept, very important. The photons that pass through the patient without any interaction are called transmitted primary photons. These photons retain accurate positional information. They strike the detector at the correct location. So the useful image information comes mainly from the transmitted primary photons. This is very important FRCR exam. So the useful image information comes mainly from the transmitted primary photons. So now, as you can see, we have the useful image maintained with the detector because of the transmitted primary photons. So next, what could be if attenuation happens? So attenuation mostly is exponential process. So from I started, you get exponential, something from I equals naught, okay, to the minus more x. So this is transmitted incidental. That comes to a very important point, which is half value layer. So half value layer is the thickness of material needed to reduce the primary beam intensity by half. So the thickness of the material needed to reduce the primary beam intensity by half. All right, that depends mainly on the following. It depends on the photon energy, atomic number, density of that material, as well as the thickness of that material. Let's discuss a bit about attenuation coefficients and half value layer. The linear attenuation coefficient, which is mu, is very important to understand this part. So the linear attenuation coefficient describes the probability of photon getting attenuated per unit path of length as they pass through the material. So meaning at the X-ray or photon passes through material per unit length, they'll get attenuated. So let's assume we're passing photon or beam through air, nearly 95% of the photon will get transmitted, meaning almost only 5% of the power of the photon passing through air will be absorbed, okay, will be attenuated or stop there. 95% of it will pass through air. So when it comes to soft tissue, that will decrease dramatically. You can see only 65% of the photon, okay, only 65%. So now only 65% of the photon will get attenuated. So meaning we'll get like 65% attenuated. Here it is 65% and there it's 95%. Okay, only 95%. So what about bond? As it comes to bonds, you can say bond attenuate almost 65%, meaning only 35% of the beam of photon will pass through bond. What about iodine contrast? Iodine is a bit high because it has high atomic number of 56, and also the K8 of iodine is almost around 37.4 or 37 approximately. So only 8% will get transmitted. Most of it will be absorbed. Meaning in FRCR or anywhere you see X-ray, the white structures on X-ray are areas where fewer photons reach the detector. Meaning if a person is undergoing barium mill, the areas that you see very bright stomach filled with the barium paired white, that's mean almost 92% of the X-ray photon passing through stomach who do not reach the detector. Only 8% were transmitted. Okay, this is very important to understand the concept. And the areas that are appearing as black, okay, that means almost everything, all the photon passing through those areas were transmitted, such as lungs, such as air inside colon and others. And the gray areas, most substantial, almost half of them, okay, half of the beam were attenuated. Okay, so this is the concept, as you can see here. Okay. So now, what are the factors affecting linear attenuation coefficient? So you can say we have density, we have energy, and we have atomic number. So let us explain this into detail. So linear attenuation coefficient called, we say, like atomic number A, D, which is density, okay, over multiply over, okay, A, which is energy. Meaning that as the atomic number increases, the linear attenuation coefficient will go up. As the density increases, the linear attenuation coefficient will go up, and vice versa for energy. So linear attenuation coefficient directly proportional to the atomic number and the density, electron density of the atoms or electron density of the material. So let's say we have something that is having high atomic number and having high density will produce more linear attenuation coefficient than something that is having less density and atomic number. So this is only for teaching because the attenuation depends on the photoelectric, Compton, the coherent interactions all together, okay? So now high atomic number material will increase linear attenuation coefficient. What about the Mach, which is mass attenuation coefficient? What's happening in Mach attenuation coefficient? So mass attenuation coefficient actually relieve the impact of the linear attenuation coefficient. So as it cancel out the impact of the density. So it equals, let's say we get our Mach, that Mach equals linear attenuation coefficient, Mach, okay, equal linear attenuation coefficient, okay, divided by density, So meaning Mach in the end will equals AD of the linear attenuation coefficient over E, okay, also at the same time divided by density. If you remember, so that we say which equals AD over E, that's energy multiplied by D. We have our linear attenuation coefficient, okay, which equals linear attenuation coefficient, which equals A, just to simplify everything, A, which is atomic number multiplied by density over energy. So since Mach cancelled out the impact of density, so we can say, meaning that everything will appear equals because it cancelled out a density effect. So since there's some density effect, we can say now we have our 8 Mach, okay, so equals, okay, let's say we have Mach equal AD over energy, okay, multiplied by 1 over D. 1 over D. So this cancels. So Mach will now be equals atomic number by energy. So meaning in the Mach attenuation coefficient, only atomic number and energy matters. So atomic number, increasing atomic number increases Mach, the mass attenuation coefficient. Whereas increasing energy decreases Mach, mass attenuation coefficient. So Mach removes the effect of density, allowing material to be compared by unit mass. Okay, so now the unit is centimeters per gram. Okay, so let us discuss regarding the Hub value layer. So the Hub value layer is just defined as 0.693 over mu, which is a linear attenuation coefficient. So Hub value, so anything that is having high lack, meaning strong attenuation, will have low Hub value layer because Hub value layer is inversely proportional to the linear attenuation coefficient. Since the linear attenuation coefficient is determined by atomic number multiplied by density over energy, so the Hub value layer is in inverse relation equals energy over AD, just to simplify everything, meaning Hub value layer will increase as energy increases and decrease as with the increased in atomic number and density. So high density with the increased density or atomic number will increase linear attenuation coefficient, at the same time decreases the high value layer. Dense or high atomic number materials attenuate faster, okay, and also allow only a small amount attenuate faster and only allow a small amount to pass through. So this will lead to increase linear attenuation coefficient while decreasing the value layer. Study the concept of linear attenuation coefficient, mass attenuation coefficient, and half value layer. Let us remind ourselves that we have said only the photons that pass through the patient without any interaction, which are called transmitted primary photons, they are mainly responsible for positional information. And when it strikes the detector at the correct location, they are the one carrying the information of the body. So now, what are the types of interaction that are occurring inside the tissue? And those interactions collectively are the cause of the attenuation of the beam. The remnant of the beam that does not, okay, undergoes or underwent any interaction after subtraction of all the attenuation that happened are the ones that will carry the information, the positional information of the body, and to be represented on the detector and be converted into image. So let us take a look into those types of interactions, the main attenuation processes. So let us start with the photoelectric effect. So in the photoelectric effect, the shell, what's happening is that as the X-ray photon comes, it will hit inner electron, okay? Then that inner electron will be ejected as photoelectrons and be deposited into energy locally in the patient. And then at the same time, the electron ejected from the inner part, okay, will be deposited in the body locally as patient does. So then an outer shell electron or electron from the outer shell, we have K being ejected. The electron is tightly bounded in the inner shell, get ejected out, okay? Then another electron from the L shell or the outer electron before the K, okay, will comes or fall inside and fill this vacant empty place, okay? So the electron will come inside, fill this vacant place, okay? And then the differences will be released. So the energy differences will be ejected or will form characteristic X-ray or other electron if the energy is less. So in a nutshell, the photon comes from outside. The incident photon will hit an inner tightly bounded electron, which will be ejected, and the energy will be deposited locally. Then the outer electron from the outer shell will come and fill this vacant empty place, and the differences in the energy will be released as terrestrial radiation. This is the basics of most of the subject contrast. If the energy is low, very low, that will be instead of X-ray, we'll have a electron. If the energy is intermediate within the diagnostic range, it will be strongly leading to subject contrast and increase in dose of the patient. So the probability of photoelectron is presented as the following. Photoelectron is directly proportional to the atomic number cube over energy cube, mostly atomic number cube multiplied by density over energy cube. So anything that will have high atomic number, such as iodine, atomic number of 53, barium, atomic number of 56, bone atomic number of 14, tissue atomic number of 8 point something. So all of them, depending on the atomic number, they'll present high contrast. If the energy is high, so the higher the energy, the less the probability of photoelectric occurrence. So this is why iodine and the barium work as contrast agent. So the photoelectric is more predominant because they have very high atomic number. Okay. At the same time, iodine Ka8 is around 33.2, while the barium Ka8 is around 37.4. All of them within the diagnostic range, and photoelectric predominates. That's why they absorb most of the energy coming, and only small amount of energy will be released to the detector, and that will be presented as contrast, such as GI, and also part of the basal contrast we're using in X-rays. The next types of interaction is Compton scattering. As the X-ray photon comes and hit loosely bonded outer electron, that electron will be released, okay, will be recoiled and deflected in that direction. Whereas the X-ray photon will be scattered, okay, with lost energy and get scattered and change its direction. So we would have different form of scatter. We may have a forward that the scatter may get forward displaced or scattered or backward scattered. The forward scatter will continue to may reach the detector. At that time, it may lead to reduction in the image contrast by forming kind of foggy area on the image, representing pulse information or signal that may degrade the image quality. So all in all, the wide angle or the angle of scatter will determine depending on like whether it is backward or forward. So you can have wide angle and backward scatter because that will lead to uh, dose to the patient because backward scatter will take the photon instead of going forward toward the detector, it will go backward toward the staff that are carrying out the procedure leading to increased dose to the staff. So let's say this is a patient, okay, and they're going okay, let's say this is a patient. We have patient here, and they're going X-ray. Okay, they're there. They're to the table. Okay, this is the detector. All right. So as we have the detector here, so the photon is coming, it hit the patient, and it gets backward scatter, and the radiologist is here handling the patient. This will get exposed to the dose, increased dose, okay, because of the backward scatter. The angle of scatter is very wide. This will lead to backwards will lead to increased dose to the staff and also the entrance of his dose. But if we have uh, continue that forward scatter, that scatter will come down, may reach the detector. But at the same time, it will not be represented the same area of the information. It will take false information to the detector, leading to foggy area around the image. This is what we call it will decrease the quality of the image. So mostly Compton scatter degrades image quality and increase occupational exposure because of the backward and forward scatter. Mostly, as we say, for the staff, the backward scatter will lead to decrease dose to staff, and the forward scatter will cause problem with the image quality. And that's the basics. And so Compton scatter mostly has no value, no potent except for the dose and foggy area. The next types of interaction is coherent or inelastic. So let me say something about so in the coherent scattering, mostly the photon come, okay, it just passes and changes direction a little. So it changes direction, but no electron ejected, no ionization, no significant energy change. It has less value in diagnostic radiology. So actually contribute very small amount. The next one is the next type of interaction is what we call two of them. We have pair production and photodisintegration. So this mostly dependent as the energy become very high above the diagnostic. We can uh, so for instance, when the energy is above 1.022 mega electrovolt, that's 2 multiplied by 0.511 mega electrovolt. Muscle is the basics, the pad production, the basics of page citing, whereby the energy coming or the photon coming would become disappears near nucleus and convert it into electron and positron pair. So this is very important. We're going to discuss it in the protein, in the nuclear medicine. The next one is photon disintegration. The energy is very high, above 10 mega electrovolts. At that station, the protein interact directly with the nucleus, ejecting it will eject the nucleus, the electron neutron formation, which is neutron is very will lead to damage the damage the DNA because of its mass effect on the tissue and the DNA or protein formation. This is very high energy. So in a summary, what determines the interaction energy? So let's say photoelectric. As we said, photoelectric is inversely proportional to the energy. So high energy decreases photo energy. Atomic number, high atomic number increase favors photoelectric. And density, mostly both of them will increase. So as we have more energy, there will be less photoelectric. And at high energy, Compton predominant, and then less high atomic number, photoelectric will predominate. So mostly photoelectric predominates in high atomic number and less energy, whereas the Compton predominates in high energy with the less atomic number. Concept to understand is a remnant beam which does not undergo any interactions. So mostly, as you can see, around the tissue there will be differently attenuated. So we mentioned in the air, fat, muscle, as well as iodine. So all in all, that remnant beam that does not undergo any interaction will take the information position information of the body part that get exposed to the X-ray and determine our image. Most of the X-ray will pass transmission, almost 95% will be transmitted around A. It will be dark. Part will be a bit gray. Rab muscle will be gray. It's okay. And bone will be highest high attenuation, and highest attenuation will be bright on the X-ray. This is very important. As we move forward, and we're coming to the end of this lecture, before going to the next one, you understand that we have backwards scatter that add to the dose, and the forward that is adding to the image fogging, okay, getting decreasing the contrast of the image. So the highest scatter will lead to decreased image contrast, and that will lead to decreased quality of the image diagnostic quality of that image. So we will have to do something that will lead us to the discussion of the next part of the chapter. Only one thing from this lecture. Remember, only the remnant beam to image is important in image formation, okay? More photon behind low attenuation dark regions and vice versa. So the image or the photon passing the image form from X-ray photon only the photon emerging from the patient. Okay, we're gonna discuss next filtration, collimation, grid, and others. So from tube to tissue. Thank you so much. See you in the next lecture of the series.